Welcome to The Explainer. Today, we're diving deep into the hidden rules that power pretty much everything, from the programming languages you and I use every day to the artificial intelligence that's, reshaping our entire world.
So have you ever really thought about this? How does your computer know that parentheses is perfectly fine, but parentheses is just wrong? It seems so basic, right? But the logic behind it is actually super elegant. It all boils down to a very specific set of rules, almost like a blueprint for language structure. All right, let's get into it. Okay, so to get a handle on all these rules, we really need a map. And it turns out the best one out there for formal languages comes from the legendary linguist Noam Chomsky. It's called the Chomsky hierarchy. And what it does, brilliantly, is organize languages based on how complex they are, all the way from the simplest patterns to the most powerful constructs imaginable. So here it is, a quick look at that hierarchy. Now, if you've been following along, you'll know we've already talked about the simple stuff, patterns like email addresses. Those are handled by what are called regular grammars, down there at type 3. But today we're leveling up. We are jumping into the much more powerful world of type 2, context-free grammars. And trust me, this is where it really starts to get good.
So what's the deal with that name, context-free? What does that even mean? Well, it's actually a beautifully simple idea, but one that is incredibly powerful.
Basically, a context-free grammar is just a set of rules. And the key, the context-free part, is that a rule can be applied to a variable no matter what's going on around it. Think of these variables, we call them non-terminals, as placeholders. So if a rule says you can replace placeholder A with this other thing, you can do it anytime, anywhere you see A. It doesn't matter what comes before it or after it. And that very flexibility is the superpower that lets these grammars handle nested things, like our parenthesis problem. Okay, let's make this real with a classic example. Let's say we want to generate strings that have some number of zeros followed by the exact same number of ones. So 01, 0011, 000111, and so on. Believe it or not, you can define this whole infinite language with just two incredibly simple rules. The first one basically says, take what you have and wrap a 0 and a 1 around it. The second rule is our escape hatch. It just says, okay, we're done, replace the placeholder with nothing. Let's actually watch how this works.
And here's that process, which is called a derivation. It's really cool. You start with just the placeholder, s. You apply that first rule, and now you have 0s1. Okay, let's do it again. Right on that inner s. Now we've got 00s11. And then, to finish it off, we use that second rule to just poof, make the s in the middle disappear. And there you have it, 0011. Just think about that. With two tiny rules, we can create an endless supply of perfectly balanced strings. That's power.
So that's all pretty slick, right? But it also opens up a tricky question. In that last example, the choice was always obvious, but what happens when you've got a more complex grammar? What if there are multiple rules that you could apply at any given step? Which one does the computer choose? This right here leads to a huge problem in language design, something called ambiguity. And for programming languages, where every single detail has to be precise, ambiguity is a total disaster. And this is exactly what ambiguity looks like. Take a simple expression like a plus b times a. Depending on how you interpret the rules, you can get two totally different structures, two different parse trees. On the left, it thinks you mean a plus b, and then multiply by a. On the right, it thinks you mean a plus b times a. Those give you completely different answers. And that is why programming languages have to be so carefully designed to be unambiguous, to enforce strict rules like the order of operations we all learned in school. Okay, so we've got these grammars, which are like the blueprints. But what about the machine that actually reads the blueprint and, builds the thing? What kind of machine recognizes these languages? Well, to answer that, we have to talk about something called an automaton, which is really just a fancy word for a machine that has a very special kind of memory.
And here's a really fundamental idea. For every single context-free grammar out there, there's a machine that's its perfect match. And that machine is called a Pushdown Automaton, or PDA for short. You can pretty much think of it as a simple computer, but it's got a special kind of memory that gives it a superpower that normal, simpler machines just don't have.
And what is that special memory? It's a stack. If you've never heard of a stack, the analogy is perfect. Think of a stack of plates. You can only add a new plate to the top, and you can only take a plate off the top. The last one in is the first one out. That's it. This simple mechanism gives the machine a memory of what it just saw, which, as you can probably guess, is exactly what you need to handle those nested structures we were talking about earlier.
Okay, so let's watch how a PDA tackles our 0011 string. It's really clever. It reads the first 0 and pushes a 0 onto its stack. Then it reads the second 0 and pushes another 1 on top. Now when it sees the first 1, its job is to match it. So it looks at the top of the stack, sees a 0, and says, "Great, a match," and pops it off. It sees the second one, does the exact same thing, pops the last 0 off, and now the input string is finished, the stack is empty. That means the string is accepted. It worked. The stack acted like a perfect little counter.
So, okay, these context-free grammars and their PDA machines are clearly really powerful. But they're not all powerful. They can't do everything. In fact, they have a very specific and provable limit. So let's push the limits a bit. What about a language like this one? An equal number of A's, then B's, then C's. So ABC, AABBC, and so on. Now, a PDA could handle the A's and B's, no problem. It would just push for the A's and pop for the B's. But then, what does it do about the C's? The stack is empty now. That single stack, as powerful as it is, has a fundamental weakness. It can only really keep track of one count at a time.
Now, to actually prove that a language like this is beyond reach, computer scientists have this amazing tool called the Pumping Lemma. The idea behind it is actually pretty cool. It says that for any context-free language, if you take a long enough string, there has to be a little section in the middle that you can pump. It's like finding a little accordion bellows inside the string. You can pump it once, twice, 100 times, and the new, longer string you create should still be perfectly valid in that language.
So, here's the kicker. When you apply this to our A, N, B, N, C, N problem, that pumpable section, that little accordion, can't be big enough. It can only contain A's and B's, or B's and C's. It can't possibly contain all three at once. So what happens when you pump it? Well, you'll get more A's and B's, but the number of C's doesn't change. The whole thing goes out of balance. The pattern is destroyed. And that's the proof. That's how we know this language is not context-free. QED.
Okay, I know. Grammars, automata, pumping lemmas. This can all feel pretty theoretical, pretty abstract. But I promise you, these ideas are not just for textbooks. They are the absolute bedrock of the entire world of modern computing.
I mean it. Context-free grammars are literally everywhere. They're the engine inside the compiler that screams at you when you miss a semicolon. They define the entire structure of languages like Python, Java, C++. They're how your web browser makes sense of HTML and XML to show you a web page. They're even used in natural language processing to model how we speak. Seriously, anytime your code editor flags a syntax error, that's a context-free grammar in action.
And that really gets to the heart of why this is so powerful. It's this beautiful, almost magical idea. You start with just a handful of simple, finite rules, and from them, you can generate an infinite universe of complex, perfectly structured things. That's the real magic of formal grammars.
But let me leave you with one last kind of mind-bending thought. It turns out that some really fundamental questions about these grammars, like the ambiguity problem we just talked about, are what we call undecidable. That means we can prove that it's impossible to write a computer program that can always tell you if any given grammar is ambiguous. It just can't be done. And that reveals this profound limit, not just in our programming tools, but in the nature of computation itself. So think about that. What does it mean when a computer can't fully answer questions about the very languages it's built on?